Welcome to video 2, chapter 2. We're going to be talking about these things called density curves. This is where we're going to start taking our data and applying more of a curve to it instead of it being a blocky histogram or our stem plot, dot plot. We're going to start applying some curves to them so that they have a little bit more meaning so we can do a little bit more calculations with them. I kind of think of this as I really wanted to make this curve look like Cartman because I like South Park and he's like, Carmen, you're so fat. Shut up, I'm just big bone. So yeah, that was my little thing there with that. So density curves. Density curve is a curve that, number one, is always on or above the horizontal axis, and most importantly, has an area of exactly 1 underneath it. That just means that underneath our curve, we have 100% 1 of our data collected there. A density curve describes the overall pattern of a distribution. The area under the curve and above any range of values is the proportion of all observations that fall in that range. And we will, this part right here, if it's a little like, what on earth did Gottschalk just say there? We'll definitely get more into this next video. Okay, so don't worry about this part too much. So to start out here, the median and mean of a density curve. So first draw a left skewed distribution, a density curve that is left skewed. Well, looks something like this, except we're now going to use a nice smooth curve here. We have our tail on the left. Symmetric, something that may look approximately normal. Cool. Skewed right, something over here, we got a little bit of a tail going. Now for 2, it says label the location of the mean and median on each. Well, all right. Let's start with the easiest one here, which would be the symmetric. If we have a symmetric distribution, the mean and the median will be exactly in the middle. So right here, that guy, that's where x bar and the median are going to be located. Easy enough. When it gets into skewed left and right distributions, this is where it gets to be a little trickier. I always try to start off with maybe the median, because the median is what splits our data up 50-50. So, if I draw a line, let's say right here, does it look like this is about 50% of our data and this is maybe the other 50% of our data? I'm going to go with it and say yeah. Okay, I don't have to be exact with this. I really have no idea. So if I call this the median, then where would the mean be located? And we'd mentioned before in the last chapter that the mean chases the tail of a skewed distribution. So since this is skewed left, the mean's going to be somewhere and I have no idea where, so I'm just going to say it's right here. There's x bar. I definitely know it's going to be to the left. It's going to be less than the median. That's all that really matters at this point. For our skewed right distribution, again, I'm going to draw a line here. Maybe that's 50%, that's 50%. Maybe not quite, but it's good enough. Oh, M bar, what am I doing? M, median. And since we are skewed right, our x bar is going to chase that tail. So maybe I put it right here. I don't really know. It's a guesstimate, but I definitely know that it should be greater than the median. So the mean on a density curve is really located at the balance point. If you could imagine this thing had density to it, mass to it, and if you could balance it, just think, since this is perfectly symmetric, the median and the mean, that would be the balance point right there. Here, you got to think I don't know. To me, it's tricky. I wasn't too much of a sciencey person, but since these are more extreme values, the mean's going to be more down here, and it doesn't really look like that's the balance point necessarily. Maybe I need to scoot these over somewhat to some degree, or maybe scoot the mean over. But identifying the exact location based on a balance point is moot. Okay, moot point. Don't even really worry about locating the mean based on a balance point. But that's where technically it should be located. The mean is that equal areas, that 50-50 point, which to me is a much easier thing to find, and then you can discuss where about exactly is the mean located. So I always start with median like I did, and then figure out, is the mean going to be about at the same location, to the left or to the right of the median? If the mean and median are equal, then the density curve is symmetric. Does that mean that it must be approximately normal? No. You could have something that looks bimodal, maybe like this. It's symmetric still, and the mean and median would be located right here, right in the middle. They would still be equal. What must the total area under the curve be? So we're talking about how much area is there underneath this curve, underneath this curve. underneath this curve, underneath this curve. Again, this is one of the main properties of a density curve. And again, it must be exactly 1 or 100% all the time. Okay, if it's more than 1, if it's less than 1, it's not really a density curve. All right, now here's a density curve. It's a weird one, right? It's mostly uniform here, and then we've got some skewness going on. But here's an example of just a, kind of a weirdo density curve. So find the proportion of observations within each interval. Again, all of this under here, that's 100%. So we're not looking for everything now. We want to find, and x represents any values, okay, that are between 0 and 0.2. Well, here's 0, here's 0.2. So really, I'm wanting to find the area underneath the curve, bounded by 0.2 and 0 on the horizontal axis here. So really, I want to find the area of a triangle. Like, oh crap, man, geometry, I gotta remember how to find the area of a triangle? Dude, that's been forever ago. Well, hopefully it's not that bad. Come on, people. It's base times height divided by 2, or 1/2 base times height. Well, your base here, how long is it from 0 to 0.2? It's 0.2. How tall is this triangle? Well, this triangle is 2 tall. And then divided by 2, well, those 2's are going to cancel out, leaving me with just 0.2. So the answer to this is 0.2 is the proportion, or you could say between 0 and 0.2, there's 20% of the entire curve is right there. So let's try another one. Any value that's greater than or equal to 0.4. Well, here's 0.4. So we're talking about this line, and we want to go greater than it. So that means we get to shade anything bigger than 0.4. Now the maximum we can really go up to is only 0.6. So now we've got this shape we need to find the area of. And the first thing most of you are going to think of is, hey, that's a square. But technically it's not, okay? This is really, truly a rectangle. Doesn't look like it, but if you look at what the base and the height are, because the area of a rectangle, base times height, the base here is 0.2. What's the height? 2. It's not really the same number, so it's not really a square. So that's 0.4, which means this is 40% of the entire curve. Now, little side note here, how much is left over right here that we haven't discussed? Well, 20% and 40% make 60%. That means this little part right here is the remaining 40%, if you wanted to think of it. But that's another question altogether. So, let's clear up some space here. Now we want to know a proportion that's between 0.1 and 1.25. All right, well, here's 0.1. 1.25, well, that's way down that way. Here's the thing. The max is only a 0.6. So what is there beyond 0.6? Nothing. There's 0 beyond 0.6. So that's almost kind of like a trick question, if you will. So 0.1, we go up to our curve, we follow it all the way to where the maximum is, which is 0.6. This is the main thing we're finding. Now you know your answer is going to be a pretty decently sized number, like maybe 80, 90% in there. We could find the area of all of this, or what we might consider is, what's the area of just this little baby triangle here that we don't want, and let's subtract it from 1 or 100%. And I would really prefer to do it that way instead of finding the area of this kind of oddball shape. So let's do that. And we're going to do that a lot in terms of probability later. So this guy's another little triangle. Its base is 0.1, and its height is 1. And we got to divide triangles in half. So this is really what? That 1 doesn't really make any difference here. That's 0.05. So that little baby triangle has an area of 0.05, which means how much is the rest of this? 0.95, or 95%. And that's how you find the proportion or percentage of observations that are within certain intervals in a density curve. Later on, we'll get into the normal curve, and it's not going to work out as nicely as this, if you will. The next example here, do we really want to look at this? I don't know. What do you guys think? I don't think it's going to be that bad. Then we got, oh man, but look at all that much more stuff we got. So let's do this. Boom. You do this one. This time we have a density curve that's in the shape of a triangle. Now, since this is a density curve, you know everything underneath this triangle makes up 100% of your data. You are guaranteed that information there. Okay? So you try, this is what I have example 10 here, and we will go over it tomorrow in class. So if you want to do it at the end of the notes, that's fine. If you want to pause the video, do it now. Cool. But we must continue on. Now, the normal distribution is a specific type of density curve. It has this nice bell shape to it. So a few examples of variables that are approximately normal. We could be talking about people's heights. You know, we have some people that are shorties, we have some people that are tall, but most of the people are in the middle. Weights, same type of story. We have some very skinny people, some very heavy people, but most... Yeah, that was the bell for the end of third hour there. And IQs are actually normally distributed. You have some people that are, you know, maybe mentally handicapped, you have geniuses, and then you've got everyone else in the middle. Now, these two pictures here, you might look at them and go, hey, they're exactly the same, but there is a slight difference. We're going to take our histogram and apply this curve, but what we're going to be doing is taking all these little pieces that are above the curve and start to fill them in all those little nooks and crannies under the curve. So that now notice this, the curve itself and under it is the only thing shaded. So it's kind of like an approximation. And if you're in calculus, this should look pretty familiar to you. So some examples here. Density curves, we talked about rectangles. We did, you know, that one example you have to do is a triangle. But a normal curve is always a bell-shaped looking curve. Always. Is it always on or above the x-axis? Yes and yes. Always true for both of these. Does it have an area of exactly 1 beneath it? Yes, applies to both. Does the shaded area represent the proportion of values in that region? Yes, just like what we did earlier with those density curves and we found the areas of maybe rectangles or triangles. Is it bell-shaped? Well, density curves don't have to be, but they certainly could. In that case, when they are bell-shaped, you call them normal curves. And does it have a single peak? Again, density curves don't have to be single-peaked. As long as they have an area of 1 underneath it, that's all that matters. And normal curves are definitely single peak. There's always going to be that peak right in the middle. So that is all for the second video. Again, go back and do this specific example. We'll go over it tomorrow in class, and I will check it for credit. Adios and goodbye.